Okay, today's lesson is called Independent and Dependent Probability. Most of this is going to be a review from what you've already learned. This slide right here is literally the only new thing from our lesson, I believe. You can let me know if anything else is new as we go through it. This is just kind of a fancy word. You've heard this word before, but maybe you haven't used it in the probability context. Mutually exclusive events. Mutually exclusive. Say that out loud. Mutually exclusive. You'll hear people say that throughout your life. Two events that cannot both occur in the same trial of an experiment. For example, you have one die. You want to roll an even and a 3 at the same time. Those two events are mutually exclusive because an even number can't be 3 and 3 can't be an even number. Okay? So write that down. That's what mutually exclusive means if you ever get asked about it. So the probability would be 0, right? Probability would be 0 of rolling an even and a 3, a number that is both even and 3. So it'd kind of be like if we went back to those Venn diagrams, it'd kind of be like event A and event B. You know how we had union and intersection? Well, these have no intersection. Okay, and so you wouldn't even really need to draw them overlapping at all. Or you could say where they did overlap, it would be empty. The sample space would be empty there. Okay, so A and B have no overlap. That's what it would look like pictorially of mutually exclusive. All right, so let's see if we can determine whether these events are mutually exclusive or overlapping. This is the fun stuff. Okay, buying a red fruit and buying a banana. Don't play devil's advocate here. Just normal answers only. What do you think? Mutually exclusive. Most bananas aren't red. If you've seen a red banana, I don't even want to hear about it. Okay, next one. Rolling an odd number and a number less than 3. Mutually exclusive or overlapping? This is on a number cube from 1 to 6. Yep, there's an overlap. What is the overlap here? 1. Very good. All right. Choosing a student in geometry and choosing a 10th grader. Well, if it was from your class, it would be mutually exclusive, right? But from all of my students, it would definitely be overlapping. I have a lot of students who are 10th graders. So that one goes in. Okay, what about this one? Drawing a jack and drawing a red card. Mutually exclusive or overlapping? Are some jacks also red? Yes. So overlapping. I just had to put this one in there. Sorry about that. Voting for Trump and voting Democratic. When people watch the recorded lesson in the future, when it's like an old recorded lesson, they're going to be like, what? They're not even going to remember. Mutually exclusive. Trump is not Democratic right now. He could change his mind tomorrow, right? No. So that you can't do that at the same time. Okay? Okay. All right. Write this down. Independent events versus dependent events. I'm not having you write down the formal definition of each of these. I just want you to write down an example. Independent is when your first trial does not affect your second trial at all. Dependent is when your first trial has an effect on the second one. So, in other words, the second trial depends on what happened in the first trial. My daughters, sometimes after dinner, when they need like a little treat, we let them have one M&M. So we have this big thing of M&Ms, and they get to pick one. And so one kid will pick one, and then the next kid will pick one, but then she'll look at hers, and she'll look at the other kids, and she'll change her mind and put it back and want to match her sister, and so she'll put it back. Anyways, drawing M&Ms. The first person, once they choose an M&M and they eat it, that has now changed your sample space. It's changed your pool of opportunities. Yeah, only one. And so, so it changes the probability that that second kid can draw the same color or whatever. Tossing a coin multiple times. Another one that's not surprising, that's independent is probability of like the sex of your child. So even though I had a girl, and then I had a girl, and even though we were like, are we going to get a boy? Are we going to get a boy? I had a girl again. It doesn't really matter. Each time the probability is independent. What you're going to have is a 50-50 chance every time, supposedly. Okay? All right, let's do the same thing. Let's sort these based off of their independence or dependence. Oh, here's the actual fancy definitions, if that matters to you. Start with this one. Picking a red, then blue, then white sock, I guess we're patriotic today, from a drawer to pack in a suitcase. I want to pick red, and then blue, and then white. Good, it is dependent, because you're packing, you're putting them in a suitcase. Since you're not putting the socks back in the drawer, you're changing your sample space every time you choose a pair of socks out of there. Okay? Selecting 2 face cards when the first card is replaced. It's like, I want to choose a face card, I want to put it back, and then I want to try to choose a face card again. The key word there is replaced, right? That is independent. Once you put the card back, your sample space is back to normal. Has not changed. Selecting a white bead, not replacing it, and then selecting a red bead. Keyword, not replacing it, right? Probability that Sarah will get a blue gumball after Chris and Mario got green ones. When you get a gumball out of a gumball machine, do you put it back? No, you do not. So let's move this over. That one is also dependent. Once that gumball comes out, you eat the gumball. I don't care what colors we're picking. It is dependent because the sample space has changed. All right, now some super easy, very basic examples. What's the probability of flipping a coin and landing on tails and then rolling a 4 on a die? Independent or dependent? What are those probabilities? Good. Completely independent probabilities. Flipping a coin, 1 out of 2. Rolling a 4, 1 out of 6. When 2 probabilities are independent of each other and you want them both to happen, you multiply them. That's not an X, that's multiply. Anyways, you multiply them. So you have a 1 in 12 chance of doing both of those things in a row. When you want 2 independent things to happen, you multiply them. Well, rather, 2 events, any 2 events to happen in a row, you multiply them actually. What's the probability of selecting a card that is a heart and then selecting a card that is black without replacement from a standard deck of cards? Keyword, without replacement. So you have to be careful about our denominator. We have to be careful to make sure that this is a dependent probability problem. All right, probability number 1. I'm going to pick a heart. How many hearts are there? 13. So that's situation number 1. Situation number 2, I did not replace the card. So that's what people forget to do sometimes. They forget to subtract 1 from the denominator. So I only have 51 cards in my deck now, and I want to select a card that's black. Now the first time I selected a heart, so I haven't changed the number of cards that are black, right? That is important to think about. There's still the same number of black cards because I'm counting on the fact that I selected a heart. How many are black? Half the deck is black. So half of 52 is black, okay? A lot of times we put our answers as fractions. Let's go crazy and put this one as a percent. So we're going to multiply 13 divided by 52 times 26 divided by 51. 12.7%. I will round it to a whole number. You have a 13% chance of getting a heart and then a black card. All right. The table shows 60 elementary students that were polled. What is the probability a student knows how to swim? So on these, you will be asked to use a few tables on your homework tonight. And you just need to know how to read the table correctly. You need to know what is my total and what is my favorable. That's what probability is all about. Favorable over total. Okay, what's the probability a student knows how to swim? So we're going to take that out of all the students polled. How many students were polled? 60. What's the probability they know how to swim? How many of them know how to swim? Yeah, so you have to be careful. We want the total number of students who know how to swim. And it looks like 40 out of 60 know how to swim. So what would that reduce to? 2/3, I believe. So 2 out of 3 students know how to swim. That's probably pretty accurate, right? Okay, next one. A student that knows how to swim does not know how to ride a bike. That's an example of a dependent probability. Okay, a student that knows how to swim. You now have your total right there. They have to know how to swim, so be careful. This is not out of 60. This is out of 40. They have to know how to swim. Now we want to know how many of those don't know how to ride a bike. 10 out of 40, 1 in 4. Is that okay? Our sample space changed. Our total changed. It wasn't out of all the kids. It was out of the ones that know how to swim. Okay, last one. A student knows how to swim and knows how to ride a bike. What's the probability? Knows how to swim and knows how to ride a bike. That sounds like intersection from our first day, right? So it's not union. It's not knows how to swim or ride a bike. They have to be able to do both. Knows how to swim and knows how to ride a bike. There are 60 students total. How many of them know how to do both? So you just find where those intersect in your table. Knows how to swim, knows how to ride a bike. Where this one meets this one is right here. It looks like 30 of them. So half of the students can do both. Good job. Okay, last one. Use the dartboard below to make up a probability question. Let's make one up together. We'll do probability of landing in the circle, but not in the square. You don't have to write it like this. I just made up that notation. So we want to know, we throw a dart at our dartboard, and what's the probability that we land here? So you should be able to calculate any of these areas. This is called geometric probability. It's a fancy way of just saying put the area of where you want to land over the total area. Let's do the total area first. What is the area of that dartboard? I think we're assuming that it is a square. Okay, so we've got our square, 30 by 30. So the total possibilities that we could land is 900 square meters. And now we need to do favorable. So to do favorable, we would want to do the area of the circle minus the area of the square. The area of the circle, pi r squared. What about the area of the square? 10 root 2. Is everyone okay with what I did there? The side of the square is 10 root 2. How do you find the area of a square? Side squared. Okay, we're not going to do this one geometry case style. We're not going to do exact where Miss Tanton makes you keep all the radicals and keep all the pies. Let's do this one for real, okay? So it looks like when we put this into our calculator, which I am allowing you to do, we get about 114 square meters. So when we divide that out, the probability would be 12.7% chance that we land in the shaded region. You should be able to do this problem no matter what I ask you. Land in the triangle but not the circle. Land in this empty space of the square, so on and so forth. That is geometric probability. You just put the area of the shaded region over the total area of the figure. Okay?